Welcome back. We have studied the predictor-corrector method in our last lecture. That was sort of an adaptive method. And now what we're going to do is to see how these approximation methods behave when the step size goes to 0. So that's the topic of our today's lecture. Let me start sharing these slides. I hope you can see the slides now. So various methods have been presented so far in this theme for approximating the solution to an initial value problem. Although there are a number of techniques which are available, but we have chosen very few methods. And the methods that have been chosen here, they have been chosen for some reasons. The reasons are that these methods typically satisfy three criteria. The very first criteria is that the development of these methods that we studied was clear enough so that it could be understood how these methods work and why these methods work. There was some natural way of looking at all these things. Okay. Second was that one or more of these methods will give satisfactory results for most of the problems which are encountered by students. So number one, these methods are easier to understand. Number two, these methods work. That's the second reason. Third reason is that if there are some other advanced methods and complex techniques, then they are based on one or a combination of these methods. So these methods are in some sense the stepping stones of other advanced or complex techniques. So that's why we have chosen these methods. Okay, now what we go towards doing is that why these methods are expected to give satisfactory results. That's what we would want to see. So one-step difference method with local truncation error tau I h is said to be consistent with the differential equation it approximates if you have that the maximum of the tau i's for all the nodes, maximum of the local truncation errors goes to 0 as h goes to 0. So this is what we do. Typically h is chosen by looking at b minus a upon capital N. So once you choose a capital N, then you are going to look at all the truncation errors, all the local truncation errors for that particular step size h. And that will typically be in terms of h. And what then we would want to see is whether these local truncation errors go to 0 as h goes to 0. This is what we want to see. The maximum of the local truncation errors should go to 0 as h goes to 0, because local truncation errors, what do? Local truncation errors assume that your computation up to the ith step is correct, and then it computes the error that may happen in the I plus 1 step. So this is a local property. Okay, so what it does, if your method is consistent, then the difference method will approach the differential equation. The difference equation will approach the differential equation when the step size goes to 0. This is what we will have when the local truncation error goes to 0. Okay, and this is a consistent method. This is what we would expect. Consistent method should be that your difference equation somehow goes close to the differential equation as you take smaller and smaller h. That is what is expected, and this is how. So the paragraph which is given after the definition, that is some sort of motivation to defining our consistency in that way. Okay, however, it's a local measure because tau I h is after all a local measure. It's a local truncation error. What we should actually be looking at, a more realistic measure of analyzing the effects of making h small, would be to determine the global effect. So you will look at the accumulated errors and then see how you have the change. So this is the maximum error of the method over the entire range of approximation. And here the only assumption will be on the initial value. We are not going to assume like local truncation errors where some initial steps are correct and then you compute the error. No, we are not going to do that. We will start with the initial approximation, which is anyway given by the statement of the initial value problem. And then then on we look at the errors, and there we have a measure. So the definition would be, it's not now consistent, but it is what is called convergent. So a one-step difference equation method is said to be convergent with respect to the differential equation it approximates if this global error goes to 0 as h goes to 0. What is the global error? Global error is this yti minus wi, and you are taking the maximum over all of that, and we want that to go to 0. So consistency is a local measure. You know, you will perhaps have a consistent method which may not always be convergent, but convergence will imply consistency, because convergence means that the global error is 0. Then the local error should go to 0. Local error is part of the global error. Okay. So what we are looking at is that the global error should go to 0. So in fact, we have studied the Euler's method, and let's check the convergence of Euler's method. This is actually, the global error is something that we have derived in our lectures. That maximum of yti minus wi, this is less than or equal to mh upon L e power L b minus a minus 1. Here we had ti. When you had the yti minus wi, instead of that b in the exponential, we had ti. But if it is if you are looking at the maximal one, then we replace it by b, and this is going to be an upper bound for our global error. But observe that m, l, b, and a, these are all constants. The quantity which is here in the modulus sign, this is a constant. M2 is a constant, of course. L is a constant. 2 and L, these are all both non-zero constants. So you have a constant time h. So therefore, when you are going to take the limit as h goes to 0 of the left-hand side, this is less than or equal to limit of the right-hand side as h goes to 0. But left-hand side is also bigger equal 0. It's a limit of some modulus values, limit of a non-negative set of values, and therefore this is whole thing is equal to 0. So Euler's method is a convergent method. It's a nice method compared to many other methods. Now, the other problem that exists while using the difference methods is a consequence of not using exact results. The point, this is also discussed, this has also been discussed before, which is that in practice, neither the initial conditions nor the arithmetic that is subsequently performed is represented exactly, because of the round off error associated with finite digit arithmetic. We are going to use finite digit arithmetic, and therefore there is always a round off error which we have to take care of. We had the local truncation error which gave us the consistency. We had the global error which gave us the convergent, and now we have to look at the round off error and what difference it makes to the method. So in fact, even for Euler's method, which is now a convergent method, this problem did lead to some difficulties. So this is something which we cannot simply ignore. To analyze this situation, at least in a partial sense, we will try to determine which methods are stable. So stable, what does the stability thing mean? You know, suppose you have a structure. Suppose you have a box which you have kept on the ground, and if the base of the box is big enough, and if someone comes and pushes the box slightly, the box will perhaps, vibrate. It will move here and there, but eventually it will again settle down. It's not going to topple over. Whereas if you have some structure which has a very small base, but it has a very good height, and if someone comes and pushes it, then the structure is likely to topple. That is not stable. So stability should be something which says that a small change or perturbations in the initial conditions should produce correspondingly small changes in the subsequent approximations. So small push should not lead to the box being toppled. Whereas if you have a, let's say, an empty box which is high enough, and if you make us give a small push to it, it may topple. Whereas if you have some such a structure which is fixed to the bottom, then again, even with a small push, it will not topple. So these are what are called the stable structures. So stable structure should mean that whenever you are changing your initial conditions by a small way, the total effect should again remain small. All right, so there is now, stability is something which is very similar to the well-posedness of a problem that we have seen earlier. And we will see a result now, a theorem actually, which will guarantee that the methods are stable, and you will not be surprised to see the Lifshitz conditions coming again in that. So suppose we have this initial value problem, y prime, I'm sorry, there should be a prime here, y prime equal to f ty, a less equal t less equal b, and y a equal to alpha. This is approximated by a one-step difference method of the form w naught equal to alpha, and wi plus 1 is wi plus h phi ti wi h. There is this function phi or phi, which is your difference function. Okay. Suppose also that there is this number h naught bigger than 0 which exists such that your phi is, so the number h naught is going to give you a set, and on this set we have the condition that phi is continuous on the set and it satisfies a Lifshitz condition in the variable w with some constant on the set. So what is the set? The set is this. The set is basically the closed and bounded interval AB times the whole real line times the closed and bounded interval 0 to h naught. This is what that set is. So what do we assume? We are assuming that there is a number h naught which gives us this set A cross R, which is the vertical strip, and you are thickening the vertical strip slightly by not just taking the 0th slice, but again expanding, making it slightly thicker to go up to some constant h naught. So it's a vertical strip which is slightly thick of thickness h naught. That is what we have. Then the following three properties hold. Once again, on this vertical thick strip, we are assuming that our function phi is continuous, and moreover that it satisfies a Lifshitz condition on this thick strip, vertical infinite strip. What are the three properties? Number one is that the method is stable. That is number one. Second property is that the difference method is convergent if and only if it is consistent. So the consistency, which is a slightly weaker measure than convergence, is equivalent here provided those two conditions are satisfied. And the consistency is actually being equal to phi ty0 equal to f of ty, because this is our difference function. And when you are letting h go to 0, the difference function should correspond to the differential function, right? And that is what we have here. So the difference equation will correspond to differential equation if your corresponding function corresponds to the corresponding function there. Okay, so this is what the consistency is. So this part is anyway true. This part is simply by definition. What we have is that part 2, which is that the method is convergent if and only if it is consistent. And finally, this is a very important property. If you have a function tau such that the local truncation errors are bounded above by this function tau h in that 0 to h naught, then the global error is less than or equal to tau h upon L e power L ti minus a. So this is giving you a very nice bound on the global error y ti minus wi. This is an error which accumulates all the local errors. This is in terms of a function which is bounding the local truncation error. So in some sense, if you take the maximum, of all the local truncation errors, that is going to give you a nice bound on the global error. This is what it does. So this third part is about controlling the global error of the method by controlling its local truncation error. Of course, the bound is very advanced. The bound for the local truncation error is simply tau h, whereas here it is tau h upon L into an exponential function. But whatever it is, there is a nice bound in terms of the bound which is giving you for, which is bounding the local truncation errors. And what this third part will tell is that if you have a certain rate of convergence for your local truncation error, then the global error will also have the same convergence. If your limit going to 0 has a certain rate, then the same rate is there for the global error going to for h going to 0 as well. Okay, so let's look at another method. We had seen that Euler's method is convergent. Let's look at modified Euler method, which is actually the Runge-Kutta method of order 2, right? So this modified Euler method is given by W naught equal to alpha, and Wi plus 1 is h by 2 f of ti Wi plus f ti plus 1 Wi plus h f ti Wi. This is what we have when we are looking at the modified Euler method. We are going to verify that this method is stable. We will actually check that the previous theorem's hypothesis is satisfied by this modified Euler method. That's what we are going to check, assuming some certain conditions on our function f. Now, first of all, the difference function is this function here in the square bracket divided by 2, because you should just have h times phi. So the 1 by 2 will come in the definition of phi, and we have f of tw, which is anyway there, and there is a slight modification. What happens is that Euler method is Wi plus 1 is Wi plus h times f of tw. That's all that it gives you, and this is modified because if you ignore this modification here, right, what we get is f of tw plus f of tw, which is 2 times f of tw, and then you have the denominator 2, so they get cancelled. So this modification which I have highlighted here, if this did not exist, then you would get back your Euler's method. This is the modification. This is why it's called modified Euler method. Okay. So let's look at the Lifshitz condition. First of all, we need to take the differences whenever we have W1 and W2. Okay, we need to see that the Lifshitz condition is satisfied in the variable W. Okay, so we will simply take the right hand side differences, and we have 1 by 2 ft W1 plus 1 by 2 ft plus h W1 plus h ft W1 minus 1 by 2 ft W2 minus 1 by 2 ft plus h W2 f of W2 plus h ft W2. So this is what we have. Right? Yeah. So this t plus h is coming because we are looking at ti plus 1. So t plus h is coming because you have ti plus 1 there. Okay, so now we are going to take modulus on both sides. The left hand side modulus and right hand side we have a certain sum. So we are going to bring the terms corresponding to ftw1 and ftw2 together, and the terms corresponding to this complicated part will also be brought together. They will be put in separate moduli, and therefore the left hand side modulus will be less than or equal to the corresponding sum of the moduli on the right. So, okay, so I have omitted a step here. So let me explain that to you here. Once you have 1 by 2 mod of ftw1 minus ftw2, now the function f satisfies Lifshitz condition. Therefore, you will bring an L out and you will simply have mod of W1 minus W2. So that's what we have here. Moreover, the second thing is obtained by considering this. Again, the second variable is W1 plus H ftw1, and W2 plus HFT W2. These are the second variables, and the function anyway satisfies Lifshitz on the second variable. So once again an L comes out, and what you then get is modulus of W1 plus HFT W1 minus W2 minus HFT W2. This is what we will get. So that is what we are getting. There is an L outside. You have a W1 plus HFT W1 minus W2 minus HFT W2. Okay. Now further we see that this W1 minus W2, that can be separated out from this W1 plus HFT W1 minus W2 minus HFT W2. That can be written as mod W1 minus W2 plus mod HFT W1 minus HFT W2. And then therefore you will have a less equal sign. I told you that this less equal sign is about the right hand side of the above step and the right hand side of the corresponding step, the new step that we have. And then that W1 minus W2 with an L which has a 1 by 2 outside can be brought together with this 1 by 2 L W1 minus W2. Therefore that 1 by 2 plus 1 by 2 equal to 1, and so you just get L W1 minus W2 plus 1 by 2 L HFT W1 minus HFT W2. Now this H can be taken common on both the HFT W1 and HFT W2. Once you take H common, you will again apply that the function f satisfies Lifshitz condition. So you have one more L coming out, which will be L square, and you have mod W1 minus W2 here. And now you can simplify this in the following way. So your phi TW1H minus phi TW2H in the mod is less than or equal to a constant times mod W1 minus W2. There is no condition on H here. So for any H naught positive, the function phi satisfies the Lifshitz condition with a modified constant, which is capital L plus 1 by 2 HL square. Is your function phi continuous? Yeah, if your function f is continuous on AB cross R, then you get that the function phi is continuous on AB cross R cross 0 H naught. So the conditions of the previous theorem are satisfied. Therefore, by the above theorem, this method is a stable method. Further, when you put H equal to 0, you see that this H ft plus 0 will only give you t, and this H equal to 0 here says that the modification is cancelled. So you simply have 1 by 2 ftw plus 1 by 2 ftw, which is simply ftw, which is the differential equation. Okay, and therefore this method is consistent because by putting H equal to 0, you are getting the differential equation part. But the theorem will then say that if something is consistent and it satisfies the hypothesis, it is also convergent. So by theorem, this method is also convergent. The Euler method is convergent. Modified Euler method is also convergent. Further, the third part will say that the local truncation errors order is the same as the order of the global error. The local truncation error is big O of h square. It's a Runge-Kutta method of order 2 in any case. And therefore, by the third part of the above theorem, the convergence of this modified Euler method is also to the second order of h. So modified Euler method we have seen in some good detail. This is about one-step methods. And now there are multi-step methods, which also are the methods that we should study. But for multi-step methods, the problems involved with consistency, convergence, and stability, they are compounded because of the number of approximations involved at each step. What happens in one-step methods is that Wi plus 1 depends only on Wi. Whereas in multi-steps, you would at least take 2 of the previous approximations, and the usual methods that we have, you know, the Adams-Bashforth, Adam-Moulton, you are going to require at least 3 or 4. So the convergence is defined in the same way because it depends only on the global error, YTI minus WI, but the consistency and stability, they are defined differently. So we will not go into those details, but we will only say that the methods that we have used, namely the Adams-Bashforth and the Adams-Moulton method, they are both stable. In fact, what happens is that in case of multi-step methods, there are generalizations of stability. There is something called weakly stable, something called stable, and something called strongly stable. And these two methods are both strongly stable. So they are very good methods. That's all that we say at this point, and we will not say anything more on this. I'm just going to tell you one more nice thing, which is that our fifth theme on ordinary differential equations is now complete. If you look at the chart which I had given you initially, there are three more themes, but even essentially they all concern the linear algebra part. So we put them together and we call that as our next and essentially the last theme. It's a huge theme. We will be doing quite a lot of things in that, but this is the last theme that we are going to begin from our next lecture, which is numerical linear algebra. So that's the last theme, and we are slowly now going towards the end of our course, and hang on, it's going to get more and more interesting. Thank you, and see you in the next lecture.